name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 7. Elastic plastic analysis of thick vessels under pressure and temperature loadings. Part 1. Now in this chapter, we are going to discuss the thick vessels. Thick vessels like cylinders and spheres, okay? Hollow spheres and hollow cylinders. First of all, I'm going to consider thick hollow spheres, and the loading in here is only pressure only, okay? Internal pressure only. So we have this sphere, internal radius A, external radius B. So it's a hollow sphere. And inside it, there is a pressure loading as shown in here. This pressure loading could be due to fluid pressure which is held inside this vessel. Okay. First of all, we are going to consider the elastic stress distribution, and then we are going to add temperature loadings, pressure from outside, and then go to incipient yielding, see where the yielding starts, and then consider the plastic case as well. So from elastic, go to elastic plastic, and then to completely plastic. In here, you can see this element. Okay, we have taken an element out of this sphere like this. This element, because it's spherical, so we are going to use spherical coordinates. The coordinates in here are r, phi, and theta. Okay, as you can see, for this element here we have delta theta, and here we have delta phi, and the radius obviously is r, and for the element we have delta r in here in the radial direction, so that's r plus delta r, that's also delta r, and therefore that's delta r and that's delta r, so that is r times delta theta, and the other one is r delta phi, and also this is r plus delta r times delta phi, and this one is r plus delta r times delta theta, similar to that. So we have the geometry of this element, and the stresses acting on the element are in the r direction of obviously sigma r plus partial sigma r partial r delta r, and in the hoop direction we have sigma theta and sigma phi, and in this direction also we have sigma phi. In the hoop direction we have sigma theta. We must note that in the spherical coordinates we have axial symmetry, so that phi and theta are equal, okay, for this element. But we have written these differently so that we can distinguish between them, but they are in fact equal. So first of all, in this kind of problems, we must write our fundamental equations. One of the fundamental equations is the equilibrium equation, because as you can see, we have this internal pressure here, but nothing is happening. It's static. So we must have equilibrium equation. We must have equilibrium. So we derive the equilibrium equation. Now, if we write the equilibrium for all these forces, for instance, in the r direction, we can write sigma r times this area, okay, which is r delta phi times r delta theta, okay, that is the area, times sigma r, and this one is sigma r plus partial sigma r partial r delta r times the big area. That big area is this times that. And in the r direction, therefore, we have some components of sigma theta, sigma phi as well, but sigma theta, sigma phi are equal because we have here axial symmetry. Therefore, if you write down these equations, in the r direction, in the theta direction, and the phi direction, and for the stresses, then you will eventually get this equation. Okay, you should do that yourself. So here we have partial sigma r partial r 2 over r sigma theta minus sigma r, while we've taken sigma theta equals sigma phi. That is the equilibrium equation we obtain from such elements. Now also from previous chapters we have these epsilons, epsilon r, epsilon theta, epsilon phi. Obviously these two are equal due to axial symmetry, but for the elastic case we have this relationship. Epsilon r is equal to 1 over e sigma r minus mu times sigma theta plus sigma phi, and similarly for the others. And then also I can write down epsilon r as this relationship, because u is the displacement in the r direction, v is the displacement in the y direction, and w is the displacement in the z direction. Here we have r theta phi, obviously, for the coordinates. So I can write down epsilon r equal to partial u partial r, and also epsilon r was equal to that. So I get this partial differential equation here, and obviously sigma theta and sigma phi are equal, and in the spherical coordinates these strains are equal to u divided by r. We have this from previous studies. Okay, so very simple relationships. Therefore we put u equal to r equal to this relationship as well here. Therefore we substitute for, instead of phi, theta, okay, because due to axial symmetry. So from now on we have only two variables, theta and r. Okay, let's see. We had this before. So if we differentiate u with respect to r, partial differentiation, so partial u partial r is equal to 1 over e. Here we got 1 minus mu times sigma theta minus mu sigma r, and we have r times 1 minus mu times partial sigma theta sigma r, and minus partial sigma r partial r. Okay, because we have differentiated this. Okay, as you can see, we have multiplied this by r. Okay, u is equal to r times that. So when we get partial u to partial r, then this times r becomes 1 over e times itself, that one, and then for the because it's r times that, so we have partial u partial r, we get that, and times r times the differential, partial differential of that. So that's why we have written it like that. And therefore also this was for the epsilon theta, this is for epsilon r. We had this before in the previous page, so we could write this down as 1 over e 1 minus mu sigma theta minus mu sigma r equal to that, because partial u partial r is equal to that. That's why we have written it like that. So this is equal to that. Okay, this is from previous page, this is from this page. So we equate these two together, and from this equation we can get this relationship. Okay, putting that equal to that, we get this relationship: 1 plus mu sigma theta minus sigma r times 1 minus mu partial sigma theta partial r, etc., minus mu r partial sigma r partial r equal to 0. So that we get this relationship, and as you can see, this is a differential equation in terms of sigma theta and sigma r. So this is a differential equation. Now we had this equilibrium equation. Okay, equilibrium equation, we use these two equations. For instance, here for sigma theta minus sigma r, we could substitute r divided by 2 times partial sigma r partial r in here. Okay, so if we do that, we get this relationship here. Our relationship becomes in terms of partial differentiations with respect to r. So that from this equation we can summarize it like that: partial sigma r plus 2 sigma theta partial r is equal to 0. So this is the compatibility equation, this is the equilibrium equation. Okay, so we have two equations here in terms of sigma r and sigma theta, and partial differentiation with respect to r. So this is our compatibility equation. Now we can integrate this compatibility equation and write it like that: sigma r plus 2 sigma theta is equal to 3a1, because if we differentiate that, that's a constant. Okay, why we have written it 3a1? Because you will see later that it will help us to get the constants in a better way. Okay, we could have written it as a1, but because we know that in a few steps we need this 3, so that's why we have used partial differential of sigma r to partial r is 2 over r sigma theta minus sigma r, and because we have this sigma r in here, so it's 3a1 minus 3 sigma r divided by r, because I have substituted for sigma theta in here from there. And therefore, because this is the equilibrium equation we had before, I integrated the compatibility equation so that I can substitute for sigma theta in here. You see, the problem is that if we have an equation, partial differential equation, in terms of both unknown like sigma r and sigma theta, then we cannot solve it. So that's why we have used this equation to substitute for sigma theta, so that we get everything in sigma in terms of sigma r, and we can then obtain and solve this equation. Now this equation, partial sigma r, 3a1 minus sigma r partial r divided by r, we can integrate this equation. Okay, because we have only one unknown, which is sigma r, and therefore minus 1 over 3 ln a1 minus sigma r ln r plus c. Therefore sigma r is obtained here and is equal to a plus b over r cubed, and we have sigma r, so that we can substitute there and get sigma theta as well. See here, I have written a and b because here I had constants a1 and c, so when I integrate I get new constants. That's why I have written it as a and b. Okay, I could have written it in terms of a1, c and another constant, but I prefer to write it like this because it's simpler, right? So from this compatibility equation, equilibrium equation, we integrated and obtained sigma r and sigma theta. Now then, we have these two equations for sigma r and sigma theta, but we have two constants a and b that we should determine this constant. So we use our boundary conditions. Now, boundary conditions for the sphere with internal pressure P. At r equal to a, sigma r is minus P, because if you remember, we took the element in here and sigma r was in that direction. So sigma r is minus P because P is in that direction at this boundary. And also at r equal to b, we have no pressure. So sigma r is equal to 0 because it's a free surface. Therefore, if we put these boundary conditions in here, put r equal to a, sigma r equal to minus p, and put r equal to b, sigma r equal to 0. So we get two equations with two unknowns a and b, and therefore a and b could be determined like this. A is p divided by b cube over a cube minus 1, b is equal to minus p, b cube over a cube minus 1. Okay, therefore a and b are known. We could put them in here, and sigma r and sigma theta or sigma phi, doesn't matter, they are the same, are determined. Therefore, the elastic stress distribution are these: sigma r, sigma theta, and sigma phi for the thick hollow sphere under internal pressure. Okay, that's what we have. Now, since we have the stress distribution, we have the stress distribution. Now we can substitute here and get the strain distribution as well. So if I put sigma theta here, sigma r here, and obviously epsilon theta is u over r. So I can get the displacement as well. Therefore, as you can see here, everything is known, and I can have the displacement in terms of r. In other words, starting r equal to a up to r equal to b, any intervals between b and a in here, I can have the displacement due to the elastic stresses in here. Now let's see if we increase this pressure. And say that we reach the first yielding. Incipient yielding means the first yield. Okay, the first material that yields, sigma theta minus sigma r equal to y. Because here we have axial symmetry, it's a very simple relationship. So Tresca and Mises are the same, so we get sigma theta minus sigma r equal to y. And I can write down this stress distribution that I obtained before and put this in here. Sigma theta minus sigma r is equal to that. We can simplify these equations like that. And obviously sigma theta minus sigma r is maximum at r equal to a, because in here you can see that if you put a in here is the smallest value gives you the largest value for sigma theta minus sigma r. Okay, you can do differentiation, put it equal to 0, you get the same thing. But it's clear from this relationship that if you put r, because it's r cube on the denominator, so this value will be maximum because this value is constant. B cube over a cube minus 1 is constant, right? So b cube also is constant, so the only variable is r, which is in the denominator. So if that is the smallest value, you get the largest value for that. So it's clear, sigma theta minus sigma. But if it was not clear, you could have differentiated sigma theta minus sigma r with respect to r, put it equal 0, and see where you get the maximum. But from this relationship, it's very clear. Therefore, if we put here r equal to a, sigma theta minus sigma r becomes maximum equal to y, and we get this relationship. Okay, we get this relationship. Note that here I have put P equal to Py, because for the incipient yielding, the first yield, the pressure reaches a certain value, which is Py, and so Py becomes equal to that if we simplify this relationship. And if A is very smaller than B, then it means that this AQ over BQ tends to 0, and therefore we get Py equal to 2y over 3. That is the incipient yielding for the cavity inside. Okay, this could be, for instance, a small cavity in a large body under pressure. For instance, in castings, when we cast a part, sometimes some gases cannot escape and are encapsulated in a very small area. Okay, so that we call it, in such a case, then we say A is very smaller than B, and we can treat it like that a small cavity under pressure. Then the pressure inside that small cavity, if it reaches 2y over 3, then the material yields in that part. Okay, so that could be a useful one, but the relationship for the hollow thick sphere is that under internal pressure. Okay, so far we have obtained a stress distribution, a strain distribution in the elastic region, and also incipient yielding.